How are we doing? You got hard copies and stuff you're turning in. That's handy to me. I would like screenshots of the graphs that you got from your boy A series. Thank you. All right. Questions about anything? Okay. Yeah, that's fine. Yeah, that works. Yeah, I just want to see the graphs so you see what the final results are. Questions at all over anything? All right. Well, let's finish up what we were talking about with Monte Carlo simulation. Then I'm going to hand out your last major assignment and talk about that. Then that's not like fun. Everybody's thrilled to pieces. Great. All right. So last time we were talking a little bit about how we can use Monte Carlo simulation to help us find areas of different things. We're going to do some more of that today as well. But let's talk about a slightly different approach that we might take if we're doing some integration problems with Monte Carlo simulation by thinking about what, pardon me, what you did back in Calc 1 and then extend it to other notions with like what we did in Calc 2 and Calc 3. So if you're just trying to integrate a function over an interval, remember what you did was your first idea, what we did back in Calc 1 was you thought about taking the area, well, you're trying to get an approximation for the area under the curve and then make the approximations better and better idea, right? So the way you did that was that you sliced up your x-axis into pieces, picked points in each of those subintervals, whatever they happen to be, and used those points as heights of rectangles, right? Agree with that? Cool. All right. So when you did that, you talked about dividing it up into intervals and then picking a point in the first subinterval, the second subinterval, the third subinterval, and so on down the line. Another way to think about it, though, it could have been that I'm in the interval from A to B. Let's just pick a bunch of random points. Don't worry about the order to start with. Pick a bunch of random points, and then you could have put those random points in order, right? And then if you pick n points and you line them up in order, you can come up with n different subintervals as you go along, right? Now, it might be the case that your subintervals might have to change size, but if your subintervals if there's enough subintervals, your intervals will be small enough that you might as well just treat them like they're all the same size anyway, right? So another way that you could attack this problem is exactly well, not exactly, but kind of how like you attack the problem back in Calc 1, is that you can find your sample points, find the heights of your rectangles using those sample points. Your base is still going to be whatever the delta x is, which you can think of as the b minus a over the n. That was what you did in Calc 1, right? So you can attack it the exact same way with a Monte Carlo simulation. If you think about it as picking the points and then putting the points in order and having the points determine your subintervals for you, essentially. Okay. Again, it's not quite exactly the same because you might not have equal subintervals, but you should have small subintervals if you're picking points that are uniformly spread out across the interval, not, clustering them at one end or the other, right? If they're uniformly spread out, and if they're uniformly spread out, then all of your subintervals should be getting really, really small, so you might as well say that they're all the same width and call it b minus a over delta, or b minus a over n again, like you did for your delta x. I know, there's a little hand waving there, but it makes sense that it would work. So let's say we attack a problem like that, kind of like what we talked about last time. If you've got say we do the same integral we talked about last time. Of course, I don't remember what the numbers were. I think it was the integral from 0 to 2 of square root of 1 plus x cubed dx. That sounds like one that I tried last time. Okay. Instead of worrying about, in this case, what the biggest values were, what the smallest values were, so you get that bounding rectangle and then compute a percentage of points that are in there, let's just do it more straightforwardly, where we can talk about picking your n points, plugging them in, adding them up, and then multiplying by the delta x. Okay? We're going to pick n points, whatever we want, and we can define what the n we want. Pick n points randomly in the interval from 0 to 2. Doesn't matter what it is. We'll compute b minus a over n, that's your delta x approximation, right? Times the sum of all of those heights. And this will give us our approximation for our, in this case, well, I wrote 0 to 2. I should have wrote a to b to be more general. Let me go back and change that. And that'll give us our approximation that we want. This will give us kind of our general idea. We'll pick the endpoints randomly. I also should say uniformly in there. I don't want to cluster somewhere because that's going to be bad approximations if I have clustering, right? I want to do a uniform random sample. I want to show you an example of somehow how you might get clustering if you don't do your randomness correctly in a little bit. Okay. Sometimes you want clustering depending on what you're trying to simulate, right? For example, if you're trying to model something that has to do with, say, people's lifetimes, you probably want to cluster deaths later on as opposed to deaths early on, right? Well, hopefully, you'd rather cluster it later on than earlier on, right? So, depending on what you're trying to simulate, you might use a different distribution, a different probability distribution based on your situation, right? Right now, the only thing we're going to worry about is a uniform distribution because if I want to try to approximate the area under the curve, I want to make sure that I have a spread out set of points across my interval. All right. So let's see if we can do this in Excel real quick. If you have some programming experience, you should be able to code this up pretty quickly as well. I know some. Devin said the other day you did some Monte Carlo simulation. Like Austin did. Somebody did. I don't remember which one of you said it, but somebody said it. Okay. It was Austin? I'm sorry. My apologies. I overcredited you? I'm sorry. All right. So let's create that set. In this case, remember last time we had to create some X's and some Y's because we were putting that bounding box around the area that we were interested in and then computed a percentage of points that landed in the area, right? If we do this method, I really do just need to calculate some X's and plug them into the function. So again, remember our command for that is that rand array command. Let's use 5,000 points, just arbitrary, not 50,000 points. Let's use 5,000 points, just some arbitrary number that I'm picking there. I want one column because I only need their X's. And again, I give it a minimum value and a maximum value. If you're picking between 0 and 1, we don't need to put those in because the defaults are 0 and 1. But if you want to change the interval, then you need to change those. Yeah. All right, so, pardon me. Now we can calculate the function values. The function that we had in this case was square root of 1 plus the x value that we generated cubed. From each of those points we just created, we're just going to plug it into the function, just like what you did in Calc 1. Those are the heights of your rectangles, right? Okay. So that's the first one. Let's copy, and then remember how we paste all the way down. I don't know why it's trying to make a Teams phone call. That's weird. Do the Control Shift End, and that'll take us all the way down to the bottom of the list, and we can hit Enter. Those are the function values, pardon me, for all 5,000 points we generated. What do we want to do with those function values? Sum them up. Good. So I'll add up the column C1 to C5000. I'm going to do this in steps. You could go ahead and multiply this by your delta x as well, but I'll just put that in the next column so you can see it in stages. You can do it all in one step if you want. Oh, the B column. Thank you. Sorry. I don't know why, but see, it was going to tell me circular if I did that. Thank you. Try that again. Don't use the C column. I would have told you something about having a circular reference. So there should be the sum of all of those. Now you want to multiply that by the delta x value. In this case, you're going to do your length of the interval divided by how many points you have. That's what the delta x is going to be. Okay? The length of the interval divided by how many points, because you're just taking the interval and dividing it into that many pieces, right? Okay. The length of the interval was 2, and you've got 5,000 pieces. Of course, I could have just done it a little bit more simply and divided by 2,500, but just to illustrate where that fraction's coming from. Yeah? Got a little over 3. I don't remember how that compared to what we got last time. Should be close. Better than close. Otherwise, we got something wrong. And again, if I just want to rerun this several times in Excel, I can just, you can do, anytime Excel does a new computation, it regenerates random numbers. So the fast way that I think to do it is just hit Control C and then just hit Control V off some cell that's not being used. And then just hit Control V over and over again, and you can see all sorts of different trials being ran. And it gives you some simulation ideas. Is that okay? This is just another way that we can do some simulation ideas to help us get an approximation for the integral. We're pretty confident the integral is around 3.2-ish, right? Maybe you would run several simulations and average the values to try to get an idea of what it might be. That's the idea of doing this. And again, if you've got it programmed already, it's a pretty quick and easy way to get an approximation. Just through simulation rather than having to go through different integration techniques or what have you. Not that you don't have approximate integration techniques, but it's a nice way to illustrate simulation ideas. This okay? Good news is, well, maybe not necessarily good news, but good news is that we can apply this to multiple integration as well. Okay? All right, so let's see if we can do a multiple integral. This is number 11b in your text. No, yeah, it's B. That's what I wanted to do. It has the integral from 1 to 4, integral from 2 to 5 of x squared minus y squared plus xy minus 3 dx, dx dy. So let's see if we can apply this principle to the same ideas that we just, apply this principle to an iterated integral using the same principles that we were just doing with a single integral. So remember when you started iterated integrals, you think about having some function, some surface, I should say, about all I can draw in 3 dimensions is a surface is a bump. You can do a sphere. That's about all I got. Okay. So I've got some function, z of x is a function of x and y. And remember, you've got some region down here in the xy plane. And then remember that you do basically the 2-dimensional analog of slicing of an interval in the plane, right? So you slice up this direction, you slice up this direction, you pick points in each of those little subintervals you just made, and then calculate your function value and use that as the height of a box, right? And then you add up all those boxes, right? Agree with that? Okay. So when you did that as a definition of your double integral, remember that your double integral over the region was approximately the double sum of all your points plugged in and then times delta x times delta y, right? You did a double Riemann sum to get that approximation. Yeah. Hopefully it sounds vaguely familiar. All right. So same idea though. We remember when you did this in Calc 2, you did it as slice up the region, then pick the points and plug them in, right? We're going to go the other way. We're going to pick the random points, let the random points give us the number of regions, and then plug those points into the function. Okay? So again, think about the points being spread out all over the region and then make the grid around the point. So there's only one point in each piece of the grid. Right? Notice the number of little squares, rectangles, whatever that you'll get will be the number of points you have. Because each point there you have 1 point in each rectangle, right? So your number of rectangles will be n again. And basically what you're doing is you're dividing up the entire area of the region into n rectangles, right? So this delta x, delta y piece, you can think of as being, this will be equal to the area of your region divided by the number of points. You're going to divide the area into, say, 5,000 rectangles because you generated 5,000 points. Then that delta x, delta y piece, remember that was the computation of the area of the little rectangle. We're going to approximate that area of the little rectangle just by saying I've divided the total area into that many points. Does that make sense? Okay. So if we go back to this problem then, we're going to pick the number of points and plug those into the function and add them up, just like what we did for the single integral, right? But instead of multiplying by length of the interval over, length of the interval over the number of points, we're going to do the area of that rectangle over the number of points. Does that make sense? Okay. So, when we do that in this case, notice the area of your rectangle is 3 times 3. You get 9 there, right? So when we do this, in this case, we'll just multiply by 9 over 5,000. when we do this add up. So the process, though, is exactly the same that we just did in the previous example. So let's pop back over to Excel. Let's open up a new sheet. Let's zoom in so you can see what I'm typing. Now, this is a function of two variables, so we really do need to plug in, pardon me, we really do need to plug in an x and plug in a y, right? So I do need to generate a list of x's and a list of y's. Our x's, I want to do 5,000 points again. I'm picking that arbitrarily. Your x's went from 1 to 4, so I'll use the 1 as the min and 4 as the max. Bless you. Same command that we did before, right? That's just the x's. How is that going to change for the y's? It'd be 2 to 5, right? So again, same command, but we'll use 2 to 5 for your min and your max. Bless you. It's the exact same command except it did 1 and 4. Bless you. Yeah, it's literally the same exact command. The only thing is that change here is the min and the max. So it's 1 to 4. Yes. Say that again. Yes. Yeah. I guess technically the way the problem was written, these were the way the problems were written was dx dy. So these technically are your y's and these are your x's, right? Because if I write it on the board, it was written integral 1 to 4, integral 2 to 5. Right? That was how it was written. So these are your x's and these are your y's. That matters for what we're going to plug into the function. Okay. I've got it backwards. Okay. Oops. What the heck just happened? Why didn't you create a whole... There it was. I'm going to insert a row so I can label that so I just remember what we have since I did it backward. At least in my brain it's backward now, yeah? We agree? Okay. So remember your function was x squared minus y, I'll write that down too. X squared minus y squared plus xy minus 3. That was the function. Okay. So in this cell here, I want to plug the values into the function, but I've got them, again, I've got them reversed. So I need to do b2 squared minus a2 squared, because that's x squared minus y squared, the way we generated them, plus the product of the two minus 3. I should have put them in the other way around. I wasn't thinking about it when I generated the list of numbers. Sorry about that. That was why I went ahead and added in a row so that we could label which ones are the x's and y's to help us remember. Generally speaking, I probably would have put the x's first and then the y's. So far so good? Again, we need to copy that all the way down. So I'll hit Control C and then Control Shift End to get to the bottom of the list and hit Enter. What do we want to do with all those values now? Sum them up. Good. Since I added a row, right, I popped in an extra row, my first value starts at C2 now, not C1. My last value now is at 5001. I had to adjust my indices since I put in a row. Sure. Everybody's numbers should look different. They should be close. I don't know. The sum should be close. But the values in this column could look remarkably different depending on how it generates points at any given time. At the end, your sum should look close, but your numbers in order may look completely different than what they do on the screen in that column C. Well, they better look completely different in columns A and B. If we're doing random numbers, if your numbers are close to my numbers, then something's really goofy going on. Or you should play Powerball, one of the two. Yep. All right, so now we want to take this value. We said the total area was 9, right? And there was 5,000 points that we used. Get about 104. So whatever you're getting is about 104-ish. Cool. Yeah. Right. So we need to take the sum and multiply it by the area divided by the number of points. So the area of the rectangle is 9 and divided it by 5,000. You got 11. Yes. No, you might have gotten 11. You didn't have to copy that. You just need to do that with myself. You just determined where was B1 squared minus A1 squared. There's an extra piece there. That's why you get minus A1 squared in there. So you'll need to copy that down. That's okay? Yeah. B1 squared, that's right. Oops. Here's going on. This for referencing this cell below. That's weird. I don't think it's gonna matter much, but you want to see 5,000, yeah. You can go to the next one. Let's see here. Yeah, I'll go ahead and fix it all the way down and see what happens. That's weird. There you go. That was what was causing it.
Yeah. Can I see
D? D is the sum of the C column.
Okay. So it would be widely different because it's random numbers. Right?
Yeah, it shouldn't be. That shouldn't be wildly different. Your sum should be close. Let me see here. C. You only summed 1,000 of them. Did you only get 1,000 points to start with? Yeah. Okay. That's fine. That's fine. Let's see what your C column says. I didn't change the order. Did you change it around?
Yeah.
Did you change it all the way down?
Let's see.
2 to 5. Your houses and 1 to 4. That's what it was. Yep. That's what it was.
Yeah.
There we go.
There we go.
There it is. All right. Phew. All right. Other questions on that one? Yes. That's okay. That could be completely what should be close is your sum, which is in column D, which is close, right? And your E should be close, which it was. Yeah, the numbers in column C might be completely different than what mine are. Oh. Other questions? All right, let's do a triple integral. Sound like fun? Yay! All right. So let's say we have, pardon me, this is 11A in your book. -1 to 1, -1 to 1, -1 to 1, x squared minus y squared minus z squared, dx, dy, dz. See if you can figure that one out. Work on it for a few minutes and see if you can figure it out. Ready, chat? Yeah. So in this particular one, since your x's and your y's and your z's all are between -1 to 1, I can create 3 columns at once with the same exact bounds. Remember that the entry in the second spot here in your random array is number of columns to make. If you want your random numbers to all be within the same interval, you can just make that number of columns. So since they all go from -1 to 1, I might as well just use the 3 and not have to do 3 separate commands. Is that okay? All right. After we create the numbers, what do we want to do next? Yeah, plug them into the function. Cool. So I'll do a1 squared minus b1 squared minus c1 squared. Oops. And not hit the wrong key with my big fat finger. Squared. Yeah. And then I want to copy that down. Ooh, hit the wrong button. Control Shift N, not Control Shift Down arrow. Control Shift Down arrow will take you all the way to the last row, last possible row of the spreadsheet, which is more than 1 million rows. Don't hit Control Shift Down arrow. Well. Control Shift End, yes, will take you to the end of the list that's there. Did it not work?
Not for me, apparently. I'm not sure what I'm doing.
End, yeah. End. END, yes.
Yeah. Well, my home and my end here are the same button, so that's unfortunate.
Oh. What goes next? Sum them up. Good. In this case, we're using 5,000 points again, so I'll use 5,000. If you use a different number of points, that'll be a different length, right? And then, multiply by the area over number of points. In this case, area really is volume, right? Because I got a 3-dimensional region that we're integrating over. What's the volume of this box? 8. Good. Yeah, multiply by 8 and divide by 5,000. Is that what people are getting? About -2.6-ish? Cool. Should just be the sum of the D column. Literally just add it up. What is your D column? Those are your function values. Oh, you want to be. Sorry, yep, those are the function values. There you go. Yep. Oops, I'm sorry. Yeah? Let's see if we can tack a couple more that are area type problems. So this one's not an integral. But it is a problem in your book. I'm just pulling problems out of your book now because they're just fine for doing these types of problems. All right. So this is number 10 in your book. They give you that your x's are between 0 and 1. Your y's are between 10 and 13. You also want your y's to be greater than 12 cosine x, and they want your y's to be greater than or equal to 10 plus x cubed. And it asks you to find the area. Well, estimate the area. I'll say find. Better word probably is approximate the area. To help a little bit, let's get a graph of what the area must look like that we're talking about. So we want, see if I can do this if I remember correctly. It doesn't do an and for me. If you type in the double ampersand, it'll put an and symbol in GeoGebra as well. 0 less than x less than 1 and 10 less than y less than 13. All right. There we go. There's the area of the region we're looking for. So here's your 12 cosine x curve, that bottom one there. Here's your 10 plus x cubed curve there. 0 to 1 for the x's, 10 to 13 for the y's. Which plan of attack that we've talked about so far might be helpful in doing this? Do you think we want to do the integration tack? Or do you think we want to do the, let's pick a bounding rectangle tack and then calculate the percentage of points that land in the region? The rectangle one, right? Let's do the rectangle idea here, right? Because I actually see a rectangle, right? I see a rectangle that bounds my area. Okay, so the first thing, let's create a list of points, x's and y's, that land in our rectangle. So we can go back and do that in Excel. Oh, fine. I'll use the mouse then. Well, oh, it's because I'm still in the cell. That's why. We zoom in again. Let's create 5,000 x's that are between 0 and 1 in our first column. And let's create 5,000 y's between 10 and 13 in our second column. Now let's attack this like we did last time. We're going to calculate whether or not the point that we generated is in the region that we want, right? So remember we did that with that if command last time? I have two conditions that we want to met, right? We want the y coordinate to be bigger than 12 cosine x, and we want the y coordinate to be bigger than 10 plus x cubed. We want both of those conditions to be met, right? So in my first piece here for my if statement, I'm going to use the and command to do that. So I want the y coordinate, which is in B1, to be greater than or equal to 12 times the cosine of the x coordinate, which is in A1. And we also want the y coordinate, B1, to be greater than or equal to 10 plus the x coordinate, which is in A1 cubed. Again, that and condition there is because I have two conditions that need to be met. You can actually use the and function to do as many conditions that you need to be met as possible. It'll cut you off at some point because Excel won't accept a whole bunch of that. For example, if you do nested ifs, it'll only go 8 deep. If you try to nest an if more than 8, it'll kill it. I've done it. Anyway, the and command here is a y greater than or equal to 12 cosine x, y greater than or equal to 10 plus x cubed. That's what those two conditions are. Again, and if you need multiple conditions, separate each condition with a comma. Okay? If the conditions are met, then the points in the region, and I want to count number of points in the region, so I'll make that equal to 1. Otherwise, the points not in the region, I'll make it equal to 0. So again, this just tells us whether or not, and you could use true or false, by the way, if you wanted to. We're just going to count how many things are actually in the region. I just like 1s and 0s because I can deal with the numbers then. Because I could just add the 1s. I could just add up this column now. I'm going to use the COUNTIF command just to practice that again. But with using 1s and 0s, I could just do the sum of that column. That'll give me how many are in there, right? So again, now let's copy this down. Not that. There we go. Again, there's 2 ways to get how many 1s are in there. I just want to practice that COUNTIF command. It's a nice command to be able to use in Excel. The COUNTIF command just says how many things in an array are equal to the thing that you're looking for, or meet a condition that you're looking for. Okay. Again, since we used 1s and 0s, just to illustrate my point, I could have also just done the sum. It gives me the same value, right? I'm using COUNTIF just to practice a different command. We've already practiced the sum command. All right, so again, we want to calculate the number of points that actually land in our region that we're interested in, right? So that is what we calculated here. Divided by the total number of points, that gives us a percentage of points, right? So that's the percentage of the region that's taken up. I need to multiply that by the area of the region, right? Since this is a rectangle, that's pretty straightforward, right? 1 by 3. So I just need to multiply it by 3. That's the total area. And get roughly 2. Yeah, did you not get 2? Oh, you did. Yeah. Yeah. Is that okay? Happy so far? Maybe not. Okay. Let's do one more of these. Let's expand it to volume. This is number 17. Well, I'm gonna modify it slightly. This one's going to ask us to approximate the volume of the ellipsoid. X squared over 4 plus y squared over 16 plus z squared over. I'm going to change it just slightly. Just modify equals 1. Just to make it a little bit more interesting. Remember, ellipsoid is just your 3-dimensional analog of being an ellipse in 2 dimensions, right? When you've got your ellipse or ellipsoid written in this form, the square root of the number in the bottom tells you how far in positive and negative direction you go from the center of the ellipsoid. Okay? Since nothing is subtracted off the x, off the y, or off the z, the center of the ellipsoid is the origin. So this ellipsoid is going to go 2 units front back in the x direction, 4 units left right in the y direction, 3 units up down in the z direction. That's what those numbers in the denominator tell you when it's written like that. So you'll get something that looks like this, and then it comes out this way and goes back that way. Football-ish. Not as pointy at the end, but football-ish. Right? Agreed? Okay. So we could do this through a Monte Carlo method with integrals, or we could do this with a Monte Carlo method of bound it in a box and do a percentage of points that are in the box. Which way do you want to attack it? You want to do it by integration, or do you want to do it with a box around it? A box around it, I think, is a little bit easier. If I want to do this with integration and do volumes of integrals, I would need to solve this for z and write it as a double integral, right? And then I also have to pick out random points in the region that we're underneath. That's underneath the surface. And then I have to calculate the area of that region that's underneath, and it's already rounded off, right? Boxes are much easier to deal with for volumes, aren't they? Right. Either method will work. I just think the bounding box method works better. Does that make sense? Okay. All right. So same idea like we just did. But in this case, we need to create a bunch of x's, a bunch of y's, and a bunch of z's. Again, I'm just defaulting to 5,000 points. You can use whatever you want. More points should give you better approximations, right? Because you're taking up more of the region. But the process is the same. If I use the first column here for the x's, what do your x's run through? And well, if I want to find the whole thing, it's -2 to 2, right? You could do the positive and find your volume in the first octant and then do what? If you make all your x's, y's, and z's positive, what could you do to that value to find the entire volume? There's a lot of symmetry here. If I could use this part that's in the first octant, what would I need to do with that volume? Multiply by 8. Yeah, exactly. You can do it that way too. Let's just do it all at once. Let's go -2 to 2. Your y's go from -4 to 4. Good. All right. And your z's go from -3 to 3. Good. So we've generated 5,000 x coordinates, 5,000 y coordinates, 5,000 z coordinates to give us 5,000 points. Great. I want to see how many of those points land in the ellipsoid, on the inside of the ellipsoid. In this condition, we only need one condition in this case. What condition has to be met by these points? When you plug the point in here, what needs to happen? Needs to be between. If I plug the whole point into this side of the left-hand side of the equation, what has to happen? It needs to be not quite equal to 1 because that would be on the surface. It just needs to be less than 1 to be on the inside, right? If you set it equal to 1, you're going to get a bunch of zeros. The chances that you actually got something where it's actually on the surface of the ellipsoid, not good. Okay, so we want to make it less than or equal to 1. So I can just write it as a1 squared over 4 plus b1 squared over 16 plus z1 squared over 9 is less than or equal to 1. I don't want to set it equal to 1 because you're going to have a bunch of zeros. Again, if you actually get something that's actually equal to 1 here, go play the Powerball. Okay? You're on a hot streak. Like those exist. Anyway. Okay. There's only the one condition here, so I didn't need that and command like we had before. Right? I only have the one condition that needs to be met. Here's the condition. There's the it's true or false here, right? Take ones and zeros again. What are you doing? Copy that all the way down. Turn it. Keep doing that. Stop it. You hit the right key. There we go. Count how many ones there are. Again, since we're using ones and zeros, you could use the sum command. I'm just reminding what the COUNTIF command looks like. So of the 5,000 points we generated, nearly 4, it is on my screen, nearly 4,000 of them landed inside the ellipsoid. So that's the percentage of the points that land in the ellipsoid. We take that value divided by 5,000. To find the volume, we need to multiply by the volume of the box we use to bound it. What size of box do we have here? 4 by 8 by 6, right? Two out back, that's 4. 3 left and right, that's 6. Sorry, 4 left and right, that's 8. 3 up and down, that's 6, right? So 4 times 8 times 6. And I don't even have to do the arithmetic. I can just put it into Excel just like that. Right? Okay. About 150-ish. Is that what you're getting? What's that? D?
C1 should be C1, right?
Oh, crap. Yep, sure it should. Thanks. That's my problem. I hit the wrong letter. Thank you. How about 101? That better? Is that more better? Good. 4 better? Sorry. Didn't mean to be hard that. The C is right here. I don't know why it's C. Probably because I was thinking C.
It is the Z points.
It is the Z points. I mean, and Z kind of sounds like C. Z? Is okay? Is process okay with doing these? Let's do one more that's slightly different. We can do other fun things with these. Pardon me. And it also, I want to also illustrate one more thing out of this. So this is actually problem number 2 on page 504. The problem asks you to find the average distance between 2 randomly selected points in the unit circle. Yes. Yeah.
After you do like your count
Mm-hmm.
what do you multiply by?
So you're going to divide by the number of points, and I give you the percentage. then you multiply by the volume of the thing that you use to balance the whole thing. So in this case, we used a box that was 4 by 8 by 6. So I multiply by 4 times 8 times 6. Okay.
Yes, mine is at the volume of the number of points before and then it was multiplied by the number. On the first one, I thought it was like 8 of 5,000.
It was. We did. I just wrote it the other way. I wrote divided by 5,000 and multiplied by. Yeah. It's the same. Yeah. I just wrote it that way because in the first way, when we started today, we were thinking about doing it as a delta x, and so you think about the length of the interval divided by n.
Okay.
And in this case, we were calculating a percentage of points that fell inside what we were looking for, and that percentage of points was in that big box. And so that was why we did it the other way around, just because that was the way we were thinking about the problem. But it's literally the exact same thing. You're exactly right. Yep. Okay. All right. So I want to calculate random points inside the unit circle. Okay. So one thing that you might think that you would want to do is like, oh, maybe I can be clever, and instead of thinking about x's and y's, I could generate some r's and thetas and use polar coordinates. That may be something you might think might be clever. Okay? It's the wrong way to do it. Let me show you why. Okay? All right. So, what's that?
I don't like the distance.
So, let's calculate, just to show you what goes wrong. Okay? Let's calculate, I'm going to do 10,000 R values between 0 and 1. Okay? And then I'm also going to do 10,000 theta values between 0 and 2 pi. Okay. You don't have to do this particular part. I just want to show you what goes wrong and why we don't want to do it this way. Okay. Remember, though, if you want to refer to pi in Excel, everything in Excel that's built in is thought of as a function. So pi is a function with no argument. And put parentheses in there. If you just type the word pi and don't put the parentheses, it'll give you an error. So you have to call it as a function. I need to convert these points to x and y coordinates to illustrate what's going on. Remember, in polar, your x is the r times cosine of theta, right? And your y is the r times sine of theta. You really don't have to follow along with this part on Excel because you're not going to do this because it's wrong. Okay? But I want to show you why it's wrong. Okay? All right. All right. Now I've generated 10,000 XY coordinates. Okay? When I do I'm going to put a scatter plot in here. Ooh, that was ugly. That's not what I wanted it to do. Let me change the number of points here. Okay. Because that doesn't illustrate what I wanted it to do. Let's try again. Let me start over. Let me generate 1,000 points instead of 10,000. 10,000 was too many and those dots are too big as part of the problem. I thought I did 5,000 in my office and it was fine, but whatever. It won't take me that long to do. Again. I told you if you didn't get the parentheses in there for the pi, it wouldn't like it. Try again here. Hopefully this works this time, because I did it in my office, on my screen in my office, it was just fine. All right, here we go. At least it's a little bit better. You see if I zoom out maybe a little bit, it'll illustrate what I want. That's a little bit better. Let me pull it this way. Do those look like they are evenly, I know it doesn't look like even a circle because of the scale, but do those look like those points are evenly distributed around the unit circle? No, they're clustered here. The reason why, of course, is the farther you get away from the origin, the R values get bigger. Think about what your polar grid looks like when you graph it polar. Those polar rectangles get bigger and bigger as you go out. So everything's getting spread out farther as you get farther away you get from the origin. So these points aren't uniformly distributed across the unit circle. So even though it's clever, this gives me a random sampling of points in the unit circle, it's just not uniform in the unit circle. So this is not what you want to do for simulation. It's going to weigh the points in here much greater than it does on around the outsides. Okay. All right. So instead, pardon me. So instead, what we're going to do is just create the x's and y's between 0 and 1, like we've done before. So let's make our random array. I'll just do 5,000 points to start with. Let's take 5,000 x values and 5,000 y values that are between -1 and 1. That'll give us the unit, well, not unit square, but that'll give us a square around the unit circle, right? Okay. All right. I want to compute, again, the average distance between 2 points in the unit circle. So this would be a random sample of points x and y. I need another random sample of points x and y, don't I? So rather than 2 columns, what I really should have done was make 4 columns, right? Because I want to consider the points 2 at a time, right? So let me go back here and change the 2 to a 4, and then it'll generate 4 columns for me without having to type in something new. So far, so good? All right, I only want to calculate the distance between the points if both points are in the unit circle, okay? That's what it says for randomly selected points in the unit circle. There's no guarantees right now that those points that we've generated are in the unit circle. So what we're going to do is just simply throw out the points that aren't in the unit circle, okay? All right, so I'll use the if command here and the and command again. I want to make sure that a1 squared plus b1 squared is less than or equal to 1, and c1 squared plus d1. Yeah, I know. I hit the enter key instead of the shift key. Thanks. d1 squared is less than or equal to 1. I don't want to calculate anything unless both points are in the unit circle. So that's what that and command calculates here for us, is that the fact that we've got both points in the unit circle. If the conditions are met, again, I'll put a 1, and then otherwise I'll put a 0. Okay, just like we did before. Same command, I just want to make sure that both points are in the unit circle. Okay. Same idea. And then I just copied that down. Just like we did before. Notice that the way we've generated this time, at least on mine, first two pair of points are in the unit circle. These aren't. These are, that's not. Those all are. Right? All right, so now if they both are in the unit circle, then I want to calculate the distance between them. And if they're not, then I'm just going to use a distance of 0 and not consider it. Okay? So if E1 equals 1, again, you could use true or false, but I actually want to use the ones in this case, so I want to leave it as a 1. Okay? Then calculate the distance between them. Distance is your distance formula. I'll do A1 minus C1 squared plus B1 minus D1 squared. Right? X1 minus X2 squared plus Y2 or Y1 minus Y2 squared, or reverse order, doesn't matter. By the way, since all of these points are all coming from -1 to 1, I could have just said my A and my B were X's and my C and my D were Y's, but that also didn't check what I had for the other condition. Just have to be consistent here. All right. Okay. So again, if the points are in the unit, both points are in the unit circle. That's what this first part says here. If they're in the unit circle, calculate their distance. Otherwise, use 0. Okay? That's what this command says. All right. Copy that down. Notice we've got some values and some zeros, which makes sense, right? What do you think I want to do with all the values? And if I want to find the average distance, what do you think I want to do with all the values that are in F? Add them up, right? So I want to take the average up and then divide by how many there are. But remember, we're throwing some out, correct? Yeah, okay. So I want to do the sum of column F, which again we used 5,000 points. I want to divide that by, and this time I will use the sum command just because it's easier to type. Add up the distance. This second sum command just counts how many points we have that are in the unit circle. You could have used the countif command again, right? Either one will work since I'm using zeros and ones. On G. So again, that denominator is just adding how many ones we had in column E. So that's how many points we actually used, right? So I'm not using all 5,000 points. If you actually wanted to generate 5,000 distinct points in the unit circle, you'd have to get more points in there. Yeah. Did you get about 0.91-ish? Somewhere around there? E is just checking to see if both conditions are met. So we're checking to see the first point is in the unit circle and the second point is in the unit circle. Because if they're not both in the unit circle, then we're not going to calculate the distance between them. You can see where this might be, if you wanted to generate a certain number of points, like we actually wanted to generate 5,000 pairs of points that are in the unit circle, probably programming would be a little better to do it. Right? I could do it in Excel, it'd be a little bit more clever. So again, the simulation idea gives you ways to get at problems that might be intractable otherwise, or at least slightly more intractable. So, anyway, as promised, I want to hand out your major assignment sheet here. We can talk about it just briefly. I know we're out of time, so.
A little bit. It's really hot outside.
Yeah, I got you. All right. So we've done lots of different things this semester. We've done mainly with approximating things or getting models for things that have that might be hard to get at otherwise. We've talked about approximating curves using least squares. We've talked about interpolating curves with polynomials. We've also talked about interpolating curves with cubic splines. And then we've also talked about periodic functions and then finding Fourier series to represent repeating functions. Right? That's what your last homework was over. This combines it all together. Okay? You're going to recreate your EKG. Okay? So one of the things you have to do is measure your pulse for a minute. Okay? And then you're going to use each of the little pieces in there to approximate things. So you'll want to reach it. So the scale right now on there is set for 60 beats per minute. So you'll have to change your horizontal scale for what those little things mean. On the curved parts, you want to use at least 2 different methods that we talked about this semester to approximate those curves. Okay. So you'll pick and approximate points on there so that you can recreate those pieces. Right? You've got a grid on there, right? So you should be able to approximate some points using the grid. And then again, use a least squares polynomial, or use a cubic spline, or use polynomial interpolation to approximate the smaller parts, right? The rounded parts. The straight line parts, you can just use a straight line to do those. Once you find those functions, then you'll use your Fourier series techniques to find a periodic function that will reproduce it. That's the idea. It's also why I'm giving it to you for 2 weeks. I would not suggest trying to do this on Wednesday night before it's due. Because I get a lot of questions on the Wednesday night before it's due. I'm not going to answer it. Okay? This is not something that I would wait till the last minute on. Okay? So your exam is Tuesday, right? And I've already told you precisely what's going to be on there. There's 4 questions. Okay? Right? Check if something is a cubic spline. Create a least squares model, given a set of data, which I'll already have in Excel for you, so you don't have to retype it. Find Fourier series, not the ones where you're checking what the identities, right? Literally find Fourier series on GeoGebra, and then Monte Carlo simulation stuff like we did today. Okay? All right? I'll send you some practice problems as well for the Monte Carlo simulation, so you have to practice and give you the answers, or approximations of the answers, so you'll know what's going on. All right? See you on Tuesday, if not before. Boo, 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 boo.
It's one of the ones with the buckles on the side.
Oh, yep. Is that right? Yeah, I'll grab it. Yeah. There we go. Is it yours?
Yes.
Okay.
So we need to change
Thank you.
get for our heartbeat to 1 second, or change what was like the graph.
You want to change your heartbeat for 1 second, so that is 1 heartbeat. That's for somebody who's 60 beats per minute. You want to change it to whatever yours is. Yeah. So all that would mean is that your horizontal scale then would be whatever. So it's 1 divided by how many other beats per minute.
Yeah.
Does that make sense?
Yeah.
Okay. I'm guessing yours is lower than 60. Given being an athlete, I'm guessing it's lower than 60 is where I think heart rate.
By any chance, could I take the test Wednesday? Because my brother graduates on Monday. Okay,
That's
cool.
fine. Congrats to your brother.
Yeah. Well,
That's an odd graduation
he
day.
plays